welcome to another RDWorks Learning Lab. Before we start, I will apologise in advance if you can hear any dogs barking in the background. They happen to be my neighbour's dogs, and yeah, they're a law unto themselves. Yeah, a bit like my wife, really. Now, as I mentioned to you before, we casually decided that we'd have a look into lenses, but once I started looking at a little bit more detail, I realised I'd opened Pandora's box, and the subject is vast. And from all the research work that I've done, there is very little research work that's been done for non-metallic cutting on machines like ours. The only way I'm going to find out answers to some of the questions that I've asked is to do the work myself. Now, this is not a science laboratory, as we found out many times before, and my methods are crude, but they do get us to the point eventually. Now, this is not a scientific treatise. Right, well, let's just clear my blood, sweat and tears off of the machine, and we'll quickly go through the methods that I used to produce these results, so that if for any reason you wish to replicate them, you can do something similar. Now, in a previous session, I went through the method that I thought I was going to be using, but when I got down to the nitty-gritty, I changed all sorts of things. I tried to use the efficiency of this machine to make my testing procedure so much easier. So before we start, I must offer some serious thanks to Mr. Rainer Ding, the head man at CloudRay. So his contacts in the optics industry in China have allowed me to access lenses that are not normally commercially available. So I think we should all say serious thanks to him, because without his help we would not be gaining access to the information that we're just about to get. Okay, so here I've got my solid steel table, and in the solid steel table I've got a couple of grub screws, a couple of tapped holes that I've put in here that hold grub screws. Now, these are locations that I use when I want to do absolute coordinate work on this machine. And so I've designed this fixture which literally just drops on there. Now, normally I would screw it down and bolt it down, but in this particular instance, the fact that it's just a little bit loose is not going to cause me a problem. And what it does mean to say is that every time I want to do a focus test, I can take it out the way so that I stand no chance of doing any damage. This is the two grey cell syndrome that I was telling you about. Now, with so many lenses to test, every time I put a lens in, whether it be flat side down or flat side up, I have to set the focus. Now, setting the focus is an interesting subject. There is a focus distance that the lens is sold as, and I believe I've got a 2-inch lens in here at the moment. I can't be sure because I swap the lenses over so often. For the purpose of this exercise, I'm going to show you how I determine the lens focal distance for the speed. Now, you may remember that I've mentioned this before, that there is a thing called the real focal distance, which cannot change because it's a mechanical thing, but then we've got another focal distance which is dependent upon speed. So if you want the best focal distance for 10 millimeters a second, it will be different to the focal distance that you run at, say, 400 millimeters a second. You may or may not believe that. You'll have to try it for yourself. Now, I've got my table set to coordinate 0, and what I'm going to do, I'm going to run a program that I've written. Because the machine has got a controllable Z on it, a programmable Z axis, I can set each one of these lines to a different Z height, and that's what we've got here. If you haven't got a programmable Z, that doesn't mean to say you can't do this test. It just means to say you'll have to take a little bit more time to do it, because you'll need a step gauge like this to adjust the height of every one of these lines manually in between each test. So you'll just draw one line and then keep testing it in different positions. As I mentioned, we need to set the parameters into the right sort of speed region for the job that you're going to do. Now, in this particular instance, we're going to be cutting, so I've chosen a speed which is just 20 millimeters a second. Whether it's 10 or 20, I don't think it makes any difference to the focal distance. But it would make a difference if we went up to 400. And here I've set the power very, very low at 10%. At 20 millimeters a second, we're going to get quite a lot of burning. As I mentioned earlier, the table is set to position 0. It cannot physically come any higher. It will only ever drop down. So that means that if I set my gap here to, say, 2 millimeters, which is what I've done, the table will now drop down to different positions. Now, hopefully, 2 millimeters is too close for the focal distance. In other words, at the moment, the focus point, I suspect, is inside the material. Now you can see at each step, the table is going down by 1 millimeter. And then it comes up back to 0 again. I think 5 is definitely the thinnest line. So bearing in mind we started off with a step distance of 2, the bottom step there. By the time we add 5 to it, it means we need a 7 millimeter gap underneath that nozzle for correct focus. Okay, so I've now set my fixture up and put the program in. We've dropped the table to 55 millimeters, and 55 millimeters down is the height that this is now at 0. So this is the same as the table height now, and I've got to set the focus correctly. You remember we've just determined that the focus should be at 7 millimeters. 5, 6, 7 millimeters. Done. Okay, so we're now ready to start the test, and what will happen is it will cut squares on here at speeds of 4, 6, 8, 10, 12 millimeters a second. Then the table will raise by 3 millimeters, i.e. we're dropping the focus into the work by 3 millimeters, and it will do the same thing again. It will do 4, 6, 8, 10, 12 millimeters a second squares. Okay, so here we are looking at the gap underneath the door here. And we're running the first test very, very slowly. And as you can see, it's too slow because we're burning the gases underneath with the excess power. Now we've got plenty of smoke coming out the bottom, so we know that we're cutting through. Now look, we've lost the smoke underneath now, so we're no longer cutting through. And there we go, we've dropped the focus in now. We've got so much excess energy there that it's actually igniting the fumes. Now dropping the focus is supposed to give us a deeper cut. Can we get the last cut all the way through? Looks as though it's just about made it through, so maybe there's a hint of the truth there. The claim is that if you drop the focus into the material by roughly 1/3, a quarter to 1/3, then you will get a deeper or a faster cut. Now, the one thing that you can see is that when the focus is on the surface, we get quite nice thin cuts. They look to be about 0.2 or 0.3. But as soon as we drop the focus, you can immediately see that we've got, I don't know, 0.4, 0.5, maybe even 0.6 cut widths. So it appears. Now bear in mind I've just turned this over and it's now a mirror image. Yes, these have fallen out, these are cut through nicely. But look what happens when we get that flame underneath. We've burnt the material. Start to get a bit faster and we've done less burning. Now these are not going to drop out because I've purposely left a tag in the corners so that they don't drop out. But obviously these have burnt so much that they do drop out. But here we can see
good cuts up to here. When we've dropped the focus down, we have actually got an extra 2 millimeters a second of cut here. That's not a cut, whereas that one is. So those are the sort of results that we're looking for. Now the other thing that we're also looking for on the top of the work is the cleanliness. Now as we get to this point here, and this point here particularly, when we do not cut through, we've got nowhere for the smoke to go out the bottom of the cut. So therefore, with our air assist on, we're blowing the smoke back onto the top of the cut. These marks on every one of these start points is because we've got nowhere for the smoke to go. There is no hole, there is no exit. The only way that that smoke can come out of the cut area is upwards until we cut through, and then when we cut through we can blow the smoke out the bottom. So that's why we always have these marks at the start point of a cut. Yeah, these look pretty disreputable, don't they? So let's just take a good one, which doesn't really matter. Let's have this one. We'll pop this one out. Now just at this point here, where the external square cuts across this little cut that I put in here, we get some very strange gas flows happening just here, and we do not get a true shape of cut. I've just put that on my little sanding belt, and I've taken about 1 or 2 millimeters off the face, so that what we can now see is the true shape of the cut and what's going on inside the cut. So that summarizes the test procedure that I've gone through. We shall take pictures of the surface, we shall take pictures of the underside, we will take pictures of the cut profile. Now, I think I might have used the wrong tense there by saying we will produce pictures. Here I have several weeks worth of work with all the data stored in a PDF file. Now I've printed them out because it's necessary to continuously cross-reference back between these various pictures of different materials and lenses. So what can we do with this data now that we've got it all? There are a couple of major questions that I cover in here. I would like to answer the question, A, what happens when our laser beam passes through a lens? That's what we're trying to find out. Just what the hell is going on? Because the theory does not match the facts. And the other thing is, what's actually happening when the beam hits the work? So those are two major questions that I really am trying to understand, and I cannot find information about that available on the old big www. I've chosen 3 different materials for my testing. One of them is poplar plywood, which basically is a pretty soft wood that would represent most typical woods. Okay, there's a thin film of adhesive in there between the layers, but essentially this is 3 different, maybe even 4 different types of wood. But I suspect that what we've got a poplar layer on the top and bottom, and then we've got some other lower quality wood layers or softer type of wood layers in between. So this is the wood representative, and wood basically oxidizes. It heats up to a certain level and then it combines with the oxygen and just disappears as smoke, leaving behind carbon, which eventually has to heat up to about 3,500 degrees C to evaporate or sublimate, as they say, disappear into gas. So this is a very interesting, simple material for us to use. Now the second material is one that we're all familiar with, which is acrylic. Now acrylic is a completely different sort of material. It's a plastic, but it's a special sort of plastic in that it doesn't melt as such. There is a liquid phase to it, but almost it goes through this liquid phase very, very quickly and evaporates. It's a bit like firing the laser at a block of ice. It will change straight from solid water very quickly through a liquid phase, and then it will boil away and evaporate. This is very similar to ice, but obviously the melting temperatures and the evaporation temperatures are a lot higher. And finally, we've got this very strange product here, which is a man-made wood. I can't remember the numbers, but it's about 85% wood fibre, like this. But then there are other chemicals in there, like water, very small quantities of paraffin wax, and it's all bound together with I'm reluctant to say nasty, but it's not the best product in the world, a material which is a binder material called urea formaldehyde. Now, when you burn that, it does tend to produce some rather nasty fumes. So always make sure that you get plenty of ventilation when you're using this material. Because of its strange composition, it's neither wood nor plastic, but a combination of both. I chose this as well because this is likely to have some very interesting properties when we cut it. There was one other product that I was going to test, but I ran out of material. Now, looking at the results of all this data, I wanted to try and get eventually to the answer to what I call my A and B questions here, my big questions. But in addition to that, there were several other various questions, stroke myths, stroke old wives' tales, which I wanted to try and put to bed with this work as well. There are 6 questions here that I think we need answers to. Is there a right way to install a lens? Flat side up or flat side down? When the material thickness exceeds 6mm, dropping the focal point in the material by about 1/3 of its thickness results in a faster or deeper cut. With the test that we've just done, we saw a definite improvement here by dropping the focus in by 3mm. It was at the penalty of not a very pretty cut on the top surface. The interesting question here is, look, we've got something that looks like a cut that's almost 1mm wide at the top here, and yet underneath it's about 0.3. So what's going on? Well, we shall find out when we start looking into the details of this testing. Number 3. Is a meniscus lens more efficient at cutting than a plano convex lens? Number 4. If you pay more for your lens, do you get a better performance? Number 5. The longer the focal length, the deeper and more efficiently you can cut. I think this came from originally somebody like Universal, who did a throwaway phrase that basically said that, and it confused a lot of people. And I continually get asked this question about, can I get a deeper cut with a longer focal length lens? So the answer to that question will be hidden in here somewhere. Number 6. This is an interesting one. Non-square edges can be reduced by using a longer focal length lens. Now, this was a statement effectively put out by Trotec, and we'll refer to that later on. But these are the sorts of questions that are going to be answered with all this work. Okay, now this page here is a summary page of every single test that I've done. Basically, it breaks down into 3 blocks here. We've got 10mm plywood, we've got 8mm acrylic, and we've got 9mm MDF that run across this way. Now, in this other direction, we've got 3 types of lenses. We've got PVD, cheap Chinese, CVD, typically from USA, and the more expensive gallium arsenide lens here. So we've got 3 types of lenses, 3 types of material. Within each section of that matrix, what we've got 4 lenses, 1.5, 2, 2.5 and 4 for each material. And then within each material type, we've got a plano convex lens and a meniscus lens. It's broken down into 2 sections because we've got the plano convex flat down and the plano convex flat up. Within each one of these cells, you will see 2 numbers. Now, the 2 numbers refer to the speed at which we were able to cut through with the focus at 0, i.e. on the surface, and the second number is the speed at which we were able to cut through when the focus was dropped into the material by 3mm. So I've tried to compress as much information as I can on this one sheet. Now, apart from helping us to answer those questions, which we shall be doing in subsequent pages, there is one fairly obvious observation that you can make when you just scan your eye across these numbers. You see 8, 10, 12s here for plywood, regardless of whether or not it's a short or long focal length lens. When you start looking at acrylic, you see 6s and 8s, occasional 10, but mainly 6s and 8s. And then when you look at MDF, well, it's 6s, 4s, and a few 8s. Bearing in mind all these tests are done exactly the same power, they're exactly the same test. The only thing that's changing here is the material. Although we've got changing of lenses, there's a general pattern which clearly shows that there is a big difference in the way in which these three materials cut. So that brings us back to my question B. What's going on when the beam hits the work, the material? Why is it that we get these significant differences in material performance when we fire light at it? Those are the big questions that I will hopefully be able to answer, although it certainly won't be in this session or with this book at the moment, because I've got to do a lot of study of this data before I can come to any sort of, not conclusion, but maybe proposal. You'll see that what we've got lens flat down, and then because obviously I had to do the test the same way round, I turned the material round and did the same test this way, which is why this test is upside down to that test. I'm afraid the acrylic, because it's a white material, didn't photograph very well. The MDF is pretty disgusting in some instances, as you will see. But having said that, it is fascinating to look at some of the other data that we get, because there's some quite interesting results coming out of MDF. It may well be the best piece of material to tell us what's going on. We'll get through a little bit further into the book at answering some of the questions. You know, the one that we've seen already. When the material thickness exceeds 6 mm, dropping the focal point by a third into the material results in a faster test cut. Well, here is an analysis of the data that allows me to say, and I'll explain it over here. From plywood, better on the surface, 4. Better 3 mm into the material, 14. No difference, 14. So hey, with plywood, very thin softwood, it would appear that dropping the focus into the material has a beneficial effect. And we've seen that with this test. When we start talking about acrylic, better on the surface, 13. Better 3 mm into the material, only 2. No difference, 17. So for that material, the statement is totally wrong. You don't get any benefit by dropping the focus into the material. And for MDF, we only get 4 better, 11 better on the surface, and 17 no different. So we only get 4 out of 32 better, 2 out of 32 better, and 14 out of 32 better. Now, across a whole pattern of materials, what I'm saying is there is no general pattern to support the statement. You may well find that certain materials and certain lens combinations you can get benefits, but in general, stick with the surface focus. And there we go. So that's how these results are supposed to be read. And right at the end of this document, I've recorded all the work that I did with lens energy density. Now, there's a lot more work to be done with lens energy density, because when I start looking at this in relation to some of the results that I can initially observe in there, I can clearly see that I need to investigate not just 2 energy levels in the beam, but I've got to try and find out what's happening right down the centre of the beam. This only is a very crude test which tells me roughly what's going on. I've now got to do a lot more work to establish what's really going on. We get to the end here where basically it says, I can tell you some things, but there's a lot that we haven't yet established, and that's for the future. Now, as I may have mentioned before, my favourite lens is a 2-inch gallium arsenide. I personally find that that has been the most efficient lens for cutting. 2-inch gallium arsenide, flat face down. That's what I always use. That's my general purpose go-to cutting lens. Am I right? So we can take a look here at 2-inch gallium arsenide. Yeah, look, with the flat down, it's not the thinnest cut that we've ever seen. It's a 2-inch lens. It's, you know, but it's not a bad cut. If we take a look at flat up, it appears that maybe I should be using that gallium arsenide lens flat up, because look, I get a thinner cut. I get a more attractive cut. So let's take a look at another part of these results. There we go, 2-inch gallium arsenide lens. So let's take a look at the cuts that happen. Well, we've got a little bit of a nick at the top there. This looks nice and clean. So that little nick at the top there is what looks like the wider cut. It's not a wider cut at all, because when you look at the overall cut width here, compare it to a 0.2 thick line, which I put on here for reference every time, it's pretty good. The only thing is we're getting a lot more damage inside the cut here than we are here. We seem to have a much straighter cut here, a cleaner cut. So maybe I ought to turn my plano convex lens upside down. 2-inch gallium arsenide lens cutting to, wow, look. If I use it face side up, I get less damage inside the cut than I do when I'm using it face down. But hey, if I bury it into the material by 3mm, yeah, I get a wide cut at the bottom. Actually, this one, so yeah, there could be an advantage here, because look, I get less damage inside the cut by going in by 3mm. Now, what I'm really showing you here is the way in which you can use all this data to assess what you're doing with your lens. So here's a practical use for that data. I think from now on I'm going to be turning my 2-inch gallium arsenide lens upside down. Totally wrong, according to everything that I've previously been told. The facts are telling me something different. Okay, let's turn the machine off, because that's enough for today. Now, this document is not for the faint-hearted. It's certainly not good bedtime reading. Let me think about that a minute. If you're my age, it may be. And I suspect that there won't be thousands of people in the world that want to digest this stuff or are even interested in it. Now, this data is mine and it's for my benefit. But hey, that's selfish. This data could be useful to many, many people out there. So I'm going to make it freely available for you guys to download as a PDF file. You can go to RDWorksLab.com forum and a copy will be lodged there for you to download, or if you so wish, you can write to me directly and I will send you a copy. Now, this document is probably only chapter 1 of a very long running saga, because there is so much more to understand about lenses than I've uncovered in this book. I may well have captured the evidence, but I've got no idea who fired the gun. So we've yet to look, for example, at the detailed energy distribution within the beam after it comes out of the lens. Now, that is a very, very interesting subject, which may help to explain some of the pictures that you will see in this book. You can guess, and I can guess, at what's going on, because we've got a huge range of pictures in here that gives us clues as to what the beam might be doing. The one thing that it's not doing, it's not spreading out. It's staying really very strangely focused in a little column or tube. So there's more questions and answers in this book at the moment, but I'll leave some of those for you to debate, and I'll catch up with you in the next session. So cheerio for now, and thanks for your time.